Okay, so today I'm going to explain how to solve Leetcode 987, vertical order traversal of a binary tree. So I'm going to try to explain the intuition on how to approach this problem, what the first thoughts are, just based on looking at this example and based on like some fundamental properties of trees and any general tree algorithm that we do. So let's first read the problem. Given the root of a binary tree, calculate the vertical order traversal of the binary tree. So for each node at position row column, its left and right child will be at positions row plus 1, column minus 1, and row plus 1, column plus 1, respectively. And the root of the tree is at 0, 0. So that's basically a known, right? Your root is at 0, 0. And the vertical traversal of a binary tree is a list of top to bottom orderings, so top to bottom orderings for each column index, starting from the leftmost column and ending at the rightmost. So starting from the leftmost column and ending at the rightmost column. And there may be multiple nodes in the same row in the same column. So in such a case, sort these nodes by their values. So let's look at the first example that they show and kind of try to understand that. So in this case, 3 is our root, right? This is where we start. And at the end of our algorithm, we should be returning the nodes in a vertical order from left to right. So basically, the leftmost column is here. So that's why we see one list containing a 9. Then the next column is going to be this one because these columns are both mapping to the same column. So because of that, 3 and 15 are there. Notice that they're also sorted based on their values, right? So 3 and 15 are increasing because they both map to the same column. Similarly, in 1, 1, this is the only one in column 1, so that owns its own list. And then for column 2, 7 owns its own list, as that's the only one. So that's why we can see, and notice that the ordering is from top to bottom as well, right? So your first priority is basically the columns because you want to go left to right. From this problem, or from this example, we can see that your ordering is left to right. Ordering left to right, and that's based on columns. And additionally, you are also ordering based on the row from top to bottom, because in the problem it says a vertical order traversal top to bottom, as we saw, top to bottom orderings. So yeah, that means like our second ordering is basically going to be from top to bottom, as we can see. And in the case that there's like multiple nodes that correspond to the same like list, or that correspond to the same row and column, in that case you're basically just sorting by their value. So then you're also ordering by row. Then you order by column. Or sorry, order by value. Let's also take a look at the second example. So in here, we can see that as we go from left to right, the leftmost column is -2. That is why we have a 4 here. There's no other node in column -2. Similarly, for column -1, there is no other node in column -1, hence why it owns its own list. Notice that we're going from left to right. Then for column 0, notice how there are 3 nodes that happen to be in column 0. We have 5, 6, 1. Now from here, you are ordering them based on the row and the value. So you can see that when you do that, the values correspond to 1, 5, and 6, and that's what you have over here. Similarly for 3, there is no other column or no other node that's within the same column, right? So you're not going to be able to, you don't have to worry about anything there. It just owns its own list. Same thing with 7. So now that we understand the general idea of the problem, what's the intuition, right? Like let's sort of build the intuition for this. So the intuition for this kind of a problem is you're dealing with the tree, right? So in a tree, there's really only a couple algorithms you can use, right? There's breadth first search or depth first search, DFS or BFS. So that's like the first thing you should kind of be thinking on. The next thing is which one do you want to go about? Now, it just so happens in this problem, it doesn't matter. And I'll kind of show you just by like, let's just say I picked depth first search, right? Now, when we go in a depth first search way, looking at this problem, Depth first search, what do? You normally carve some path in going downwards, right? It's not level order like breadth first search where you're going like level by level like this. We are going depth first, right? We know that. So the next thing that we want to think about is how do we want to do our depth first search, right? Let's say we're doing our depth first search. How do we do our depth first search? How do we do our DFS? Well, there are multiple ways to do our DFS, right? You have post order, pre-order, and in order, right? Post order, that's a way. Pre-order, that's another way. And you have in order. Now, that's kind of a prerequisite. If you're doing this problem, you should know the difference between post order, pre-order, in order. If you don't, I recommend you probably learn that. But basically, when looking at this problem, what makes the most sense if we just like logically approach it? Say we start here. What do we want to do? You want to explore your nodes, right? You want to explore this node, then you want to explore that node. Okay, then maybe you want to explore that node, etc., right? But before you do that, like, yes, you want to explore these nodes, but what are you doing with this first node? You need to map it. You need to take this node right here and basically say, okay, this is my row, this is my column. If I move from this row and this column, I can either go left or I can go right. But my child node depends on some information from my parent. My child node depends on some information from my parent, right? I'm passing something from the top to the bottom. What am I passing? You're passing the row and the column from your parent, right? Passing row, column from parent to child. And in depth first search, the only order that really satisfies that when both your children require information from your parent, that is a pre-order traversal. Pre-order traversal. Pre-order supports this type, right? It's basically a top-down approach where you pass information from your parent to both your children, right? Because if I have a 2 and a 3, we both know that these are children of 1. But how do you know that this is a 1 and a negative 1? How do you know that this is a 1 and a 1? You don't, right? The only way you're going to know that piece of information is if you know where you came from. You came from your parent. You started with 0, 0, right? So that's kind of the intuition between why we're thinking between a pre-order traversal, right? So that there's that. Now, at your root, we already said you start at 0, 0. At root, start at 0, 0. Now you have two decisions. You can go left or right. Two decisions. If you go left, right, what does that mean? Yes, you increment your row because you have to go down, but left means you subtract your column. Similarly, if you go right, it's the same idea. You increment your row and you increment your column. Now, this is basically telling us the states that we want to pass down. Now we want to start thinking of states, right? Because we just said that that's the information we want to pass down. So, okay, let's think about our states. What information do I need to pass to basically know what row and column I'm in? You just need to know your node. Obviously, you need your node. Why do you need your node? It's because you need to know the value at the end of the day, because with whatever you're returning, you need to know that value, right? So you're going to need to know your node, you're going to need to know your row, and you're going to need to know your column. So that's pretty intuitive as to why those states hold. The next thing we need to think about is what are we doing when we do our pre-order traversal, right? So in a pre-order traversal, we know that you have your depth first search function, right? You have your depth first search function of some node, some row, some column or whatever, right? And we need to also think about what is our base case. So like what happens if you don't have a node? i.e., what happens if you're null? Well, if you're null, let's think about that. Let's just go back here. If you're null, right, if you try to depth first search and you have like null values over here, you can't do anything. You're just going to have to go back up. You can't do anything, right? So you're just going to return. I'm not even going to bother to return none. Why? Because I don't care. I'm not using my information returned from my children. I'm passing information down from my parent to my child, not the other way around, right? Because in a pre-order, you do your logic first, then you call your depth first search. So at this point, we need to identify what logic we're doing, what logic to do. And that itself is quite simple, right? We know the row and the column. So why don't we just have a list that holds the what's it called? The column, the row, and the value, right? You can basically have a list that'll hold those values. And then each time you visit a node, simply just add that information to the list, right? So imagine you have like a list of here, all right? What do you want to do? You just need to add the value of the node and the column and the row, right? So I can pass the column, I can pass the row, and I can pass the node dot value. Why am I doing it this way? The reason is because of what we talked about earlier. You order left to right based on the column. That's why I'm first putting the column, then the row, then the value. So that's exactly why the order I've done is in this way. And you're probably wondering, okay, I have this in a list, but that's not really going to correlate to what our final output is, right? Because we haven't done any sorting, because it told us to sort if we have multiple nodes that map to the same column. And I also haven't really explained how are you going to go left to right, right? Because I'm just adding nodes as I go. I'm not going in a particular order, only go left, then slowly go right. And we'll get to that point, right? Right now, we just want to hold all the pieces of our tree, which is the row and the column and the node. That's why I was saying it doesn't really matter if you do a depth first search or a breadth first search. You just need to visit all the nodes. And the depth first search, that's why we're doing our pre-order. But you could very much do this with a breadth first search and carry the same information. In fact, the trade-off would actually be you could use like a while loop and you're not using the auxiliary call stack. So if you had the case where it's an unbalanced binary tree, you probably wouldn't have to worry about a stack overflow. But that's kind of like beyond the scope. Like we shouldn't really worry about that for this problem. So yeah, so after we add all our nodes, right? When we add all our nodes, what's happening? Once we add all our nodes, our list is going to look something like this. We store 0, 0, 1. We store, let's just say, we store -1, 1, 2. Store -2, 2, 2, right? Basically the column, the row, and the value. So I've basically added this one, this one, this one. Then we'll add this one. And then we'll add, what's it called? This one, this one, this one. So at this point, you can basically say 0, 2, 5, and then you can add like 1, 1, 3, and then you can add 0, 2, 6, and then finally you can add 2, 2, 7. So at this point, you kind of just need to map everything to the column. And when you think mapping, what do you think? You think hash map, right? Because your objective at this point is just map the values of nodes to their column. Before we do that, though, we should sort this list. And if you sort this list, it's obviously going to be sorted automatically. I should say sort, not sorted, because we haven't done it yet. Sort by the column, the row, the value, right? Now everything is going to be fine because if anything corresponds to the same column, right, then it's automatically going to be ordered by the value after that, right? We don't really even have to worry about the case where you're going to have two nodes that map to the exact same column and same row. That's not really possible just because like it's a 2D problem. You can't have like another node just sitting there. So you don't have to worry about that case. So after you sort this, right, you basically just want to map the values of the nodes to their column, right? So how do you do that? You just have to create a hash map. And what is our hash map containing? Well, we just want each column to point to a list because in our problem output, we can see everything is mapping to a list, right? So that basically tells us that our key can be our column and our value can just be a list, right? Because everything is just going to be, every key, I should say, which is a column, is just going to be pointing to some list. So once you do that, like let's just say you add your nodes, then of course you just want to call your depth first search on the next node, which is the left. And then you could say row plus 1. This is the information we're passing down to the child, which is particularly why I said you don't need to worry about what your children are returning, because they're not returning anything. And then if you have row plus 1, column plus 1. Finally, at the end, when you call your depth first search, you're just passing it on your route, right? And then you're starting at 0, 0. But at that point, when you call this function, once it explores the whole tree, it'll populate nodes. So as we said, you want to sort your nodes. Finally, when you sort them, our objective is just finish our mapping, right? So I can make like a hash map list, some mapping, and I can basically use a default dictionary. And inside of that list, what do I want to do? I basically want to go through our nodes, and the order those nodes come in are for the column, the row, and the value in our nodes, right? What do I want to do? I just want to say the mappings for this particular column are going to correspond to some value, and that value is just v. Now that that's done, I just need to return my list. So what I can do is I can return a finalized list, and inside this list, what do I want to do? I want to point to the values. What are the values? The values are literally just going to be the lists of the values of the nodes, because each column points to a list of values, right? Because we've done our mapping. So at that point, I could just say call list. In fact, I'm going to say mapping, and I'm just going to use a shorthand expression for a for loop. You could very much do this with a separate for loop if you prefer for readability. But basically, you're going to go through your mappings, and you're going to say for column list, right, in, and we can sort our map. Why are we sorting our map? At this point, we just want to finally sort by our keys, and our keys are just our columns, because they need to go left to right, right? You're probably saying, why am I sorting again? Well, you sorted here, and that was just for your nodes to be in the same ordering with respect to values, right? But over here, when you're actually outputting, they need to be sorted exactly by the column. So you basically can just say, for your mappings, that's going to sort it by the keys, and the keys in this case are just our columns. And yeah, that's pretty much all you need for this problem. So then we'll go over the code, and we'll write it, and then we'll see that it works. Okay, so as I said, we're going to go through the code. So basically, it's the same stuff that I wrote. Your nodes are going to be ordered by the column, the row, and the value. Over here, we're going to do our pre-order traversal. If we don't see a node, just move away from it. Add the column, the row, the node value, and then explore your neighbors. Again, you could totally do this with the breadth first search. That's like another way of doing it. I just decided to do it with the depth first search. So in our depth first search, we're going to explore our tree. It'll take linear time because you have to explore every single node. Same thing with space. In the worst case, like let's just say you're dealing with an unbalanced tree where it basically becomes a linked list, then it won't be log n time. So that's basically worst case with space. Then you want to sort this. That's going to take n log n time for the n nodes that you have, creating a hash map over here, as we said. And then you basically want to map each column to a list containing the values. Over here, we're good when we add the values because they're already sorted. You don't have to worry about that. So that's why when you're able to append the value here, they're already being done sorted because you quite literally sorted your list earlier. The only reason you're sorting it one last time here is because for hash maps, the keys are never sorted, right? So that's why you're just making sure you iterate through those columns in a sorted order. And then finally, you're just going to append that list because over here, it's basically just a list, right? So if you run this, we can see that it works, and if we submit this, yeah, we can see that it works. So yeah,